Okay. So good morning, everyone. It's great to see all of you again for the second lecture on gravitational waves. Before we actually get started, I have a couple of announcements. So first of all, tomorrow, Monica and I will swap the lectures. So Monica will have the morning lecture at 9 a.m. Mountain Time, and I will take the second lecture at 10:45 a.m. Mountain Time. I also uploaded yesterday's lecture notes to the wiki, and I posted the link for this numerical relativity Einstein Toolkit School, both on the wiki and on the Slack channel. Okay, so
and that switch in schedule has been updated on the schedule. So just
Okay, wonderful. Just to remind everyone. So do you have any questions about our lecture yesterday before I get started with today? Okay, that doesn't seem to be the case. Our plan for today is to finish our discussion on gauge choices in general relativity that are particularly well suited to identify the gravitational radiation degrees of freedom and to describe gravitational waves. And then once we are done with that, we will start describing how gravitational waves propagate, how they impact matter far away from the source, and how we can actually use that to then detect gravitational waves. And for this very last part, if you have time, I think I would like to experiment a little bit with breakout rooms, but we'll talk about that in more detail when we get there. And as usual, or as I said yesterday, if you have any questions, just interrupt me or put it in the chat, whatever you feel most comfortable with. Okay, so with all that said, let me just switch to my notebook, and it should work better today because I actually found a working version of the program that I used to use in the past. So this should be much better now. And let's start with a brief recap of what we had done yesterday. So remember, we started studying gravitational radiation, and to make the problem tractable, we decided to, or I decided for you, that we will work in the weak coupling and slow motion approximation. So just to get started, today is 23rd of June. And we start with a short recap from yesterday. So remember, to study gravitational waves, we want to work in the weak coupling and slow motion approximation. That is, if you remember, we can write our space-time metric G mu nu as some background metric, and as a background we choose to use the flat metric eta mu nu plus some small perturbation h mu nu that we count with this order parameter epsilon, and the inverse metric we saw can be written in this form eta upper indices mu nu minus epsilon h mu nu. And then we would have higher order corrections here. Okay, let me just write out one thing, one operator that I think caused a little bit of confusion yesterday. So if we look at the wave operator, in general, we would have the Box operator, which is the contraction between the inverse metric G mu nu, and in general, we would have the covariant derivatives nabla nu here. So if I expand this out, I would have a first bit, which is just a flat D'Alembert, mu nu, and then we have these terms of order epsilon, h mu nu, d mu d nu, plus eta mu nu, and then we have a gamma term here, rho mu nu, computed with a perturbation times this partial derivative. plus higher order terms. So since here we are interested in the first order corrections, so terms of the order epsilon, if you apply this wave operator on our metric, then only this first term here will contribute. So let me label that as box eta. And I think the confusion yesterday arose because I was a bit lazy and didn't write this subscript here. So let me try to be a bit more consistent today and refer explicitly to the flat space wave operator. Also, one more thing, also related to the wave operator. So if I write out our wave operator in derivatives, then we would have here a minus 1 over c squared speed of light, second time derivative plus Laplacian. And again, this is probably something that we missed because we had a discussion that finding a wave equation for our perturbation also indicates that our gravitational waves travel at the speed of light. Wasn't quite as obvious because we use geometric units where we set the speed of light to 1. Yeah, so this is just a reminder that I set c equals to 1 and the Newton's constant to 1, unless I need it explicitly for order of magnitude calculation if I actually want to put numbers in. Okay, so the other item, other reminder is that we don't actually work directly with our metric perturbation H, but we use this trace reversed version or the form that coincides with gravitational potentials. So here, again, just as a reminder, so we work with the gravitational potentials. And that is, we use this H bar mu nu that's equal to our original perturbation H mu nu minus 1/2 eta mu nu. And then here we have the trace. H is a contraction between the perturbation and the background metric. Good. And what we've seen already yesterday is that we're using or can work in the harmonic gauge. So just a reminder, the harmonic gauge can be written as divergence del mu H bar mu nu, so the divergence of our gravitational potential equals to 0. And that fixes 4 independent components of our 10-component tensor. And the nice thing was a really beautiful consequence of using the harmonic gauge is that our Einstein's equations in vacuum can be written as a wave equation for these gravitational potentials. So let me just move this up a little bit here. So Einstein's equations in vacuum, and this straightforwardly extends if you have matter sources. So these Einstein's equations become a wave equation with respect to the flat wave operator acting on our gravitational potential H mu nu equals to 0. Yeah, so that's what we've done where we stopped yesterday. And what I want to do now in the first part of the lecture is use the remaining gauge freedom that we still have to really identify the gauge invariant radiative degrees of freedom in our metric. Okay, so just get up here. Yeah, we still have enough space. So that is our last section in this chapter, section 2.4. We will introduce a gauge that's known as transverse traceless gauge. So if you remember yesterday, we talked about infinitesimal diffeomorphisms that can generate a gauge transformation. So these could be written in the following form. So okay, so they could be written as some new coordinates x prime mu equals to x mu plus a generating vector xi mu that is a function of these coordinates. And if we insert that into our metric perturbation, we saw that we can write our gravitational potential h bar mu nu as h prime mu nu, so that's our transformed perturbation, plus 2 partial mu xi nu symmetrized over the indices mu and nu minus eta mu nu eta kappa lambda partial kappa xi lambda. Okay, so now let's insert that into the wave equation for our potential. Okay, let me just put a star up here. So if we do that, we find the following. Sorry, not in the gauge, in the wave equation actually. So, oops. Okay, this is what I want to do. So that is our gauge was written in this form. If we insert this and do the calculation properly, what we will find is that the harmonic gauge can be written as a divergence of our new quantity h bar prime mu nu plus a box operator, again with a flat space metric acting on our vector xi mu. So in other words, if you want to preserve the harmonic gauge, so if you want to keep this form independently of the choice of our gauge, then we find that as long as the wave equation, as the wave operator acting on our generating vector is 0. Yeah. So in other words, we have this additional freedom to choose this vector xi mu if it satisfies the wave equation. Oops. Box xi mu equals to 0. Yeah, such that the harmonic gauge is still satisfied in both systems. So to find solutions for this vector xi mu, we can expand it in the far field. That's where we are currently working in. Oops. So solutions to this wave equation are of the following form. In the far zone can be written as 0 component, say, would have a structure of 1 over r times a function alpha that is a function of t and our distance, and the spatial components xi can be written as some 1 over r times a function beta of t, beta I of t and r. Now, I will not specify these two functions, alpha and beta. Suffice it to say that we can actually choose them in a very particular way that helps us simplify our equation. In particular, we will choose these functions, alpha and beta, such that our perturbation, our gravitational potential, becomes traceless, and that the spatial components also become transverse, so are also divergenceless. And if we do that, we will actually see that only the spatial components of our perturbation contribute, and that we can further reduce our degrees of, or number of independent components in our perturbation. So let me just write that down a little bit more carefully, what I just said in words. And for that, I will go to the next slide.
I have a question.
Yep.
So I thought when you went to the harmonic gauge, you already fixed a vector field to generate some sort of diffeomorphism.
Right, but this is a kind of an additional freedom that we have here. So think of it as having two different vectors that you can choose and set.
Oh, so the total transformation is the sum of these two vector fields.
Exactly.
Okay.
Yeah, so conceptually, you're right. So we've already chosen one vector field that helped us to reduce fix four independent components, and now we are using a different vector field that will allow us to fix 4 more components. So going from 10 independent components, we will then arrive at 2 degrees of freedom that are gauge independent, that are actually physical degrees of freedom. Yeah, so that's the logic here.
Okay, thank you.
Okay, you're welcome. Okay, so yeah, let me just write down what I just said. So we can choose, and as I said, I'm not going to do that explicitly here, but if you're interested, Poisson and will have a very nice discussion about this in chapter 11. So we can choose these function alpha and beta that I just introduced, such that first of all, the perturbation is traceless. Yeah, that is our h bar equals to 0, and that implies that also the trace of the original perturbation is 0. And the second item is that we impose, so we can choose these functions such that the time-space component vanishes. That is, we can put it or choose these functions such that h0i equals to 0. Now, what are the consequences of that? Okay, let me just use arrows to indicate the consequences. So first of all, let's look at the harmonic gauge and let's look at the 0 component thereof. Right, so if we write this out, we see, so we can write it as partial 0, h00, plus partial I, h0i. Since we put h0i to be 0, means the entire component is 0. So this first part here indicates that our perturbation is spatially transverse. So, yeah, and what I mean by that is precisely that the divergence of h0i, so summed over I, equals to 0. And if you wish, this is kind of analogous to the Coulomb gauge that you can have in electromagnetism. That's just a side note. The other consequence is that if you inspect now this first term here that I have in my wiggly line, that by consequence is also 0, which means that the 0,0 component of our perturbation is time independent. Yeah. And more generally, we see that, and that comes from the transverses of the harmonic gauge, h mu 0 are constant, and we can put them to 0. That is, only our spatial components are non-zero. Okay, so all of these properties put together is what we call the transverse traceless gauge, and we will indicate that by a capital double capital T. So all of this put together forms the transverse traceless gauge, indicated by the names. Just use this here because we choose the function such that our perturbation can be traceless, and it's already transverse from this condition here. Okay, so that is partial mu h mu nu tt equals to 0, and this is the same as actually putting the original perturbation divergence thereof to 0, and it's, since we are in the traceless form, it's the same as having our gravitational potential divergence free. Okay. Yeah, so this is our transverse traceless gauge. So whenever I use this double T, that's exactly what I'm referring to. Okay, so and now we have exactly what I promised. So we, if we now go and count our degrees of freedom, then we went from having 10 independent components in our original tensor, which is a symmetric tensor. Then we used the harmonic gauge to fix 4 components. So we ended up with 6. And now we used this transverse traceless gauge to fix 4 more components. So we end up with 2 degrees of freedom. Yeah, and the gravitational waves have 2 polarizations. Okay, very good. So that's where I wanted to arrive after the discussion of the gauges. Do you have any questions up to here? Anything that you would like to go over again? Okay. If not, then let's continue and actually talk about gravitational wave propagation. That is, how do we describe the waves or wave solutions in the far field, far away from our source? And let me just start on a new page to do so. So as our next chapter, chapter 3. So gravitational wave propagation. And its impact on matter. And what I'm interested in is a system like this, where I say, okay, I have some source here, which is in a small region, source, and I have an observer or a detector far away here. Our observer. Yes, I'm interested in the distance here. We said yesterday is much larger than the characteristic wavelengths. And I'm interested in the wave solutions far away from the source that we may observe here. Okay. So, and what we have to solve for this is the wave equation h mu nu equals to 0 in the far zone. Now, if we do that, we can actually see that the solutions in the far field can very well be described by plane waves, or if you want a general solution, by a superposition of plane waves. So, okay, yeah, so the solutions to this, or any solution really, can be described by a superposition of monochromatic plane waves. That is, we would write our metric with the following ansatz, our perturbation, that we say we have some amplitude matrix that I call A mu nu, and then we have a wave solution which is exponential of I k sigma x sigma. And in the end, what we will do is actually take the real part thereof. I will work mostly with a full complex solution and then take the real part in the end. And here in the solution that or in the ansatz that I wrote down, the A mu nu is the amplitude or polarization matrix. And this K mu is our 4-wave vector. Okay, so what I want to do with you now is discuss properties of the solution using, or which are implied by the transverse traceless gauge, and then I will actually go and give a more specific example as we go along. So first of all, what are the properties of the solution? Well, first of all, because our metric perturbation itself in the transverse traceless gauge is traceless, also our polarization matrix will be traceless. Yeah, so since HTT equals to 0, also the trace of the polarization matrix that I define as eta mu nu, A mu nu equals to 0. We also have that this polarization matrix is symmetric, which follows from the fact that our perturbation, our metric itself is symmetric. And because our perturbation is only spatial, the same holds true for our polarization matrix. Yeah, so because H mu 0, TT equals to 0, we also have that H mu 0 equals to 0. Okay. So next property actually follows from this transverse condition. So this condition that partial mu H mu nu TT equals to 0 implies the following. So if I now insert our ansatz, we see, or that gives us I k mu A mu nu exponential I k sigma x sigma. So you see that the polarization matrix is orthogonal to the wave vector, or in other words, our wave vector itself is orthogonal to our metric perturbation. Yeah, so this is to 0, that is the wave vector is orthogonal to the perturbation. Okay, so next equation that we can look at is the wave equation itself. So here we would have a wave operator acting on H mu nu TT. Again, I'm not inserting everything in detail. You can do that and or verify that at home. But what we find here is that this is minus k kappa k lambda eta kappa lambda, and then we have A mu nu and the exponential. That is, we have minus, and then the norm of our wave vector k lambda times H mu nu tt itself, and because we are looking at the wave equation in vacuum, this equals to 0. So from this relation, it follows that the norm of the wave vector, that is k lambda equals to 0. So the wave vector is a null vector. Yeah, so. If we now write out the components of this wave vector, we can actually find a dispersion relation. So we can write the wave vector k mu as a term that contains the frequency and spatial components. So the fact that the wave vector is a null vector implies the following. Just go up a bit. So that implies that minus omega squared, minus the frequency squared, plus the spatial sum, the norm of the spatial wave vector equals to 0, or in other words, the frequency equals to plus or minus the norm, spatial norm of the wave vector. And here, we just insert this. Here we would have, again, the speed of light if we would reintroduce this. Yeah. And that is the dispersion relation for a wave that at least far away propagates at the speed of light. Okay. Very good. So to write out the polarization matrix explicitly, I will assume, just for simplicity, to give you an example, that our wave is propagating along the z direction, so along the k3 direction. Yeah, so the next item that we want to do is actually write out the polarization matrix explicitly for one example. So to do so, let's consider propagation along the z direction. Yeah, that is our wave vector will have the components omega, so the frequency 0, 0, and then just k3. And using our dispersion relation that we just wrote down, this is nothing else but omega 0, 0, omega here. Okay. Now, if we use the fact that we just showed before, that a mu, k mu equals to 0, then we find automatically that the components a0 mu equals to 0 and a0 mu equal to 0. So the only non-vanishing components will be the 1, 2, and 2 components. Yeah, so if we insert all the properties that I have listed on our previous slide, then the only non-vanishing components are a11, and because of the tracelessness, this is actually minus a22, and we just label that very indicatively as H with a plus. So this is what we will later on refer to as the plus polarization of our gravitational waves. Now, the other non-vanishing components are the A12 component, and because of our symmetry, this equals to A21, and we will label that as H cross. So this is what we will call the cross polarization of our gravitational waves. So if I write that in a matrix form, we will have the following: that our polarization matrix A mu nu is given by H plus minus H plus on the XX and YY component, H cross on the A1, 2, and 2, 1 component, and then everything else will be 0. Okay, yeah, and as I said, H plus and H cross are the gravitational wave polarizations. And they completely characterize our gravitational wave. Great. Okay. So having all said all of that, let's digest that a little bit and think about how these wave solutions that we have now constructed might impact matter far away. In particular, what I would like to think you about for a moment is would and how, if so, how would a gravitational wave impact a single particle? What do you think?
It wouldn't.
Mm-hmm. That's absolutely right. Yeah, so passing gravitational wave would not at all impact a single particle. And the reason for that is essentially that a single particle would move along a geodesic, and you can always find a coordinate system where the forward velocity remains or is 0 and then remains constant. That is, or in other words, if you want to think about a funny analogy, think about having like a paper boat on a small lake and putting waves through. So the boat itself will not actually move by itself and would basically stay put. So you wouldn't be able to make any characterization or any inference about the wave that may pass through. So what we do need are at least two nearby particles so that we can measure their relative motion to each other. Okay, so let me write that down and then we think about how we can describe that in a bit more detail to describe that mathematically. Yeah, so just as a so the next section here is the impact of gravitational waves on matter. And as I just mentioned, single particles are not affected. By passing a gravitational wave. That is, we need the relative motion between nearby particles. Okay, so what we will do is assume that each of these nearby particles still move on geodesics. And what we can now consider is the deviation or the change between these geodesics. I'm not going to go into any details on how to describe that, so I would refer you to standard textbooks on general relativity to do so. I will just use the equations for the geodesic deviation here for the description. Yeah, so you can describe this by the geodesic deviation. And in particular, if we take the separation vector, oops, as mu, then we can describe this as derivative d by d tau, where tau is a proper time between the particles, proper time. So we have the separation vector as mu, and then you can show that this can be related to the Riemann tensor R mu upper index, mu rho sigma lower indices, and this is contracted with the 4 velocity of our particles, u nu, u rho, and then the separation vector as sigma here. Now we will make one more assumption that we say, okay, we have nearby particles and they will move essentially with the same 4 velocity field. So let me write that here on the right-hand side as a side note. So particles, we will assume this, move with the same 4 velocity. U mu, and we will expand this 4 velocity around the rest frame. So what I mean by that is that we will take the 4 velocity to be 1, 0, 0, 0, so which describes a particle at rest, plus a small perturbation epsilon u mu. And let me just label that as 1. Now let's also remind ourselves, and again, I will give you the final result, the Riemann tensor in the TT gauge. And this is a somewhat lengthy, but conceptually straightforward calculation that you can do. And what you should find is that the Riemann tensor, and let's just look at the 0, 0 component, and I will tell you in a minute why that is. So the Riemann tensor is mu 0, 0 sigma can be written as 1/2, and then we have the second time derivative here, h mu sigma tt. Now the reason why I only wrote down this component is the following, that if we insert our assumption for the 4 velocity in our geodesic deviation equation, we will see that indeed only the R mu 0, 0 sigma component will contribute to our deviation. Yeah, at leading order. And the reason is that the Riemann tensor itself is already of order epsilon, so only the leading order component of our 4 velocity will contribute here. Okay, so let me just write that down on the next slide. So as I said, if we insert our expansion for the velocity, we will find that this equation becomes R mu 0, 0 sigma as sigma to leading order and epsilon, and then we neglect higher order terms here. So if we put all of that together, we will now find an equation for the geodesic deviation. So what we get here, we will also, we'll make one more assumption, put that on the side here. So the assumption is the following, that if we take the proper time tau, then we can actually write that as t, which is what I'm going to use at the moment, plus again higher order terms and epsilons that we neglect. So with all of that said, we can now write our geodesic deviation equation as the second time derivative of the separation vector as mu, and that equals to 1/2 second time derivative of h in the TT gauge, so perturbation in the transverse traceless gauge, mu sigma, and then we have a contraction here with our separation vector as sigma. And what we can see almost immediately, if we again assume that our wave travels along the z direction, is that only the S1 and S2 components are non-zero. So yeah. Unequal to 0. Okay. So what I would like to do next is actually solve this equation explicitly. And what I will do is consider a ring of nearby particles. So this will lead to the plots that you may already be familiar with. It's just quite convenient way to study this. So what I will look at is a ring of particles that originally, if there's no gravitational wave passing through, are really have the same distance among each other, so are properly spherical. And I will consider the two polarizations that we have seen before separately. And any more complex solution you can then find through a superposition. Okay, so in the first instance, let's just assume that we are oriented such that our cross polarization is 0 and we can focus only on the plus polarization of our gravitational wave. So this is what we are going to do here. If we insert now this, oops, sorry, this should be non-zero. Now, if you insert the plane wave solution that we've derived before into our geodesic deviation equation, we find the following. So our second time derivative of S1 or S2 is given, the equation is then plus or minus 1/2 S1, 2, and we have the second time derivative, sorry, here of H plus times this exponential e to the I k sigma x sigma. So the solution to this is the following, and again let me just write it in a compact form, where S1 or S2 as a function of time is given by 1 plus or minus, for a second solution, 1/2 H plus e to the I k sigma x sigma, and then depends on the initial value of our deviation at t equals 0. Okay, so if we consider a set of particles, they would oscillate in the x and y direction if we choose Cartesian coordinates. So our particles oscillate in the x1, x2 direction. Yeah. And what I will sketch in a moment, what we will see, that the shape of this oscillation will resemble a plus. So let me just briefly sketch that. So let's assume you have here our x1 and x2 plane, and let's assume that we have a ring of particles here that in an ideal world should be perfectly spherical. If we now assume that a gravitational wave passes through in the direction of the screen, then the particles will oscillate. And in particular, they will oscillate in this shape that they may be stretched in the x2 direction and squeezed in the x1 direction. And because my drawing is not really perfect, let me just draw a continuous line on which these particles would lie. So they would come back to their original position, then oscillate in the opposite direction, come back, etc., etc. So similarly, if we now look at the cross polarization, so if we say, okay, let's assume we are in a state where this plus polarization vanishes, only the H cross polarization is present, then we would find the following. So let me just go up a little bit. So in the second case, we say, okay, now the H cross polarization are non-zero, and we put H plus to be 0. Then the geodesic deviation equations are the following. They would be described by the second time derivative of S1 equals to 1/2 S2, second time derivative of H cross times exponential e to the I k sigma x sigma. So you get that very straightforwardly if we just insert our solution, our plane wave solution that we found for the gravitational potentials. And similarly, for the second component of the deviation of the separation vector, we have 1/2 S1, second time derivative of H cross e to the I k sigma x sigma. Okay, the solution to these equations are the following, that we have S1 component as a function of t is given by its initial value at t equals 0 plus 1/2 H cross the exponential I k sigma x sigma, and then a dependence here on the initial value for the component 2. And like analogously, the S2 component as a function of time is given by its initial value plus 1/2 H cross exponential ik sigma x sigma, and then S1 of t equals 0. Now, if we solve this equation, if we sketch the solution, we will find the following. And actually, let me just wait a moment so that those of you who write can finish their writing, and then I will continue on the next page. Okay, so let me just move on. So what you will see now is that there's the following. So again, we will start with this ring of particles, and let me, just to make it easier to draw a line. And as before, we are now assuming that our gravitational wave passes through our screen. And if it only has a cross polarization, what will happen is now that the ring of particles will start oscillating in kind of a cross shape form like this. So it may oscillate first this in this way, then have the other form, and so on and so forth. So that is particles still oscillate in this x1, x2 plane in a cross-like shape. Okay, so let me just finish this part with a couple of notes. So I think one should really realize that here it's not the particles themselves that are moving on their own. They're really following the distortion and the change in space-time itself. So remember, the very first question I asked you yesterday is, what is a gravitational wave? Yeah, so they're metric waves, they're distortions of spacetimes themselves. So the particles follow this distortion of spacetime. So they're displaced by the oscillating spacetime. So. Okay. And what you may also have noted, in particular, looking at these illustrations, is that we can actually rotate the different gravitational wave polarizations into each other. So you can see that already in the matrix form, but also here in the plots, that they can be rotated into each other, and the angle that you would need for that are 45 degrees or pi/4. So if you wanted to describe gravitational waves in a particle picture, if you wanted to look at gravitons, then you could actually relate this factor that you would get and how you rotate the different polarizations to the helicity of that particle. So again, let me just put that as a note. Yeah, so first of all, the polarizations can be rotated into each other. By an angle pi/4. And then the last item that I wanted to make, or note that I wanted to make here, is that this can be related to the helicity or spin of our field, if we were to think about our gravitational waves as gravitons. So the helicity would be determined by pi/2s, which implies that graviton is a spin-2 field. Oops. And actually, you may be more familiar with that in electromagnetism. So if you look at electromagnetic waves, they can be rotated into each other by a rotation of 90 degrees or pi/2. And their helicity indeed is spin s. So you can think of electromagnetic fields as a vector or spin-1 field, whereas a gravitational field is a spin-2 field. Yeah. And okay, so that was just a side note. And for the last about 10 minutes that I have here, I would like to go over some basic principles of gravitational wave detectors and how we can use this impact of gravitational waves on matter for gravitational wave detectors. And what I would like to do, and I think we have the time actually to do so, is a little experiment, and that's why I asked in the very beginning whether we can use breakout rooms. So I would like to split you up in groups of 5, I think is a reasonable number, and just for 2 minutes, not much longer than that. And I would like you to think about how you would design a gravitational wave detector. What would you tell a friend of yours or colleague of yours who is an experimentalist of what you need to construct if you want to measure gravitational waves? Okay, so here I would like to have some help from the organizers to just, I should be able to set up the breakout rooms myself. And I think with 8 breakout rooms, we should roughly have 5.
Do you see the breakout room option?
Yeah, I can see the breakout rooms. Let me create 7 breakout rooms, which should get 5 to 6 participants per room. As I said, really just for 2 minutes. I will stay here, and when you come back, I would like to hear your ideas of how you would design a gravitational wave detector before I tell you what's actually done currently. Okay, so let's try that. And I open all the rooms now. Okay, so let me see. I should be able to close the rooms. Okay, in 1 minute. Okay. Okay, so I think everyone should be back now. So now I want to hear your ideas of how to construct a gravitational wave detector. So let's start with the first group, which I think was Joao, Albert, Alex, and Thomas. So what's your idea? What would you do?
So I hate to say this, but you get Ray Weiss to teach general relativity and have him think of something.
Okay, sorry, Thomas. Gotcha.
Ray Weiss is an atomic physicist at MIT, as you know very well. And the story is that he invented LIGO because he had to teach general relativity.
That's wonderful. I didn't know that story. Excellent.
Oh, yeah, absolutely.
Mm-hmm.
Okay, there's some folklore for you. And then you go over to your AMO people and you have a long conversation with them. So you talk to the next lecturer and she tells you how to build one.
Yep. Wonderful. Okay, so all that said, I would still like to hear some ideas from our other groups. So I think we had Kelly, Chris, and Kishan and Xing in the next group.
Well, we discussed basics of how LIGO works. I guess fundamentally that you'll need interference of some kind. At least I couldn't really think of a way to measure gravitational waves without interference.
That's wonderful. And that's actually how it's done mostly nowadays. Other ideas. So I think I have Aninda, Annie, Peter, and Wayne here as well.
Hey, I remember I heard once about this primitive gravitational wave detector called a Weber bar, which is basically a big aluminum can, like 2 meters in size. And it was supposed to resonate when a gravitational wave passed through it. But the experiments that Weber claimed to have done with these couldn't be duplicated. But it was, in principle, something that could be used. It just turned out that it didn't actually work in practice.
That's absolutely right. And in fact, as a side note, I think there are actually still experiments using this bar idea of having this big block of material and finding a resonance as a gravitational wave passes through. And then the last group I have here is Marcus, Jonathan, Jamie, and Frick. What are your thoughts?
So yeah, so we discussed LIGO and interferometry and having 2 Armans and isolating all of the noise and all of that kind of stuff, and also thought a little bit about other ways you can detect gravitational waves, such as detecting time variations and things like pulsar timing arrays, which are pulsars are rapidly rotating neutron stars and on different locations in the sky that have a very precise clock because of their
that's absolutely
their
right.
spin
So
rates and
this
stuff.
is
Yeah.
wonderful. Yeah. I love all the different ideas or knowledge that you bring back here, because all of this is very important. And Thomas actually put in LISA as well, which is a planned space-based mission that also uses laser interferometry. So I know I only have 4 minutes left, Thomas, but I would like, or maybe 5 minutes, but I would like to take those and just go very briefly over the main ideas for the interferometer that we are using. And Thomas, it seems like you can jump in anytime here. But indeed, what we are using nowadays mostly is in the very, very basic principles, kind of Michelson-Morley interferometer that would work as follows. So, okay, yeah. And this is really a kind of current design is using laser interferometry. That is a very refined version of a Michelson-Morley interferometer. Yeah, so what we would have here is essentially a source of light. Nowadays we are using lasers here that is shot in. We have a beam splitter here, so we have light going, say, up one arm and the other arm. We have mirrors at the end of each of these arms. Light gets reflected back and recombines, interferes here, and then is measured by a photodiode detector here. Okay, so some more specs, because this looks really super simple. And the idea is if you now put your interferometer such that, in the case that no gravitational wave passes through, you basically have a null interference, you don't detect anything. Then as the wave passes through, if we were now to overlay this with our ring of particles here, the position of the mirrors would vary. So we would have this, say, squeezing and stretching and this oscillation in this, for example, in this fashion, if a wave passes through into the screen. And now, because light travels at the speed of light, this change in length would be translated in a change in arrival times. That is, you would have an interference pattern that you could then detect in your detector. So that's a very basic principle here. The length of these arms is about 3 kilometers. And yeah, so let me just give you an example of what we're actually trying to measure, because the first time you hear it, it sounds super, super simple, but it's not, right? So as I said, the length here of the arms, for LIGO at least, is about 4 kilometers. And what we are trying to measure is this relative change in length that is of the order of 10 to the minus 21. So this is typically how large a gravitational wave reaching us here on Earth would be. That is, we would essentially try to measure a change in length that is 10 to the minus 18. Even with the extra design, so what actually happens, and I'm just adding this here in gray to not overlay too much. So we actually have extensions for the light, where light is reflected back and forth to increase the effective arm length to a few hundreds of kilometers. So even in this case, what we're trying to measure is a relative change in length of 10 to the minus 16, right? So effective arm length could be of the order of a few hundred kilometers. And then what we are really trying to measure here is a change in length that is of the order of 10 to the minus 16 meters. So that this has been accomplished is really, for me, mind-blowing in the design. And what I would actually like to do, because we're at the end of our time, is stop here, finish this discussion tomorrow. So the last 2 items that I wanted to actually show you is in which range at least LIGO is most sensitive. And also, what kind of noise sources we have here in this detector that can impact our detection of gravitational waves, before I then go and discuss with you sources and production of gravitational waves tomorrow. Just one more item as well, because I wrote down here laser interferometry. There are actually active studies on using instead atom interferometry. So I know in the US there is the Magus team working on that. There's also a new team in the UK led by John Ellis and collaborators investigating a new technology to have again an interferometer with, but not with lasers, with atoms. Okay, so all that said, I will stop here. I will take any questions. I will also stay on a little bit if you would like to discuss more informally. And then I see all of you tomorrow at 10:45 Mountain Time.
Okay, thanks a lot, Helvi. Are there any questions for Helvi?
I had a question. You said that the particles don't actually move, they just follow the geometry, and I was trying to understand the difference between these two. So let's say you had a bunch of charged particles, would the electric field between them change as the gravitational wave passed through them?
Let me see. No, so I mean, the position of a particle would still, so think of it in the following way, right? So our particle does not, so we are not pushing it from the outside. It's really just following the motion in your geometry. So that's where my analogy with a like little boat on a lake comes from, right? I mean, of course, in this case, you would have surface waves, but you wouldn't give a push actively to the boat. It would just follow the geometry of your, in this case, then water surface.
The electric field would not change. Let's say you had two particles antipodal on that circle that you drew. The electric field between them, if they were both positively charged, would be constant as a function of time.
Let me think about that and get back to you.
I think it would certainly change because their proper distance is changing.
Yeah, I mean, if they're changing, then how is this? I mean, that should be a measurable quantity, right?
For a single particle, you can always choose your gauge so that that particle follows a straight line trajectory. So in that sense, a single particle, you can't detect any motion.
But if you have two, then you have a relative change in the separation.
So this is actually a measurable quantity. That you can just see if the electric field between the particles changes and measure that. And that's a way of detecting that the gravitational wave has passed through.
Yeah, so let me think about how large this effect would actually be, or maybe you can actually take that as a homework, as an exercise.
Okay, thank you.
Mm-hmm.
More questions?
What is the wavelength of these gravitational waves that
So
are detected?
no, that's an excellent question. That depends a lot on the source. So if you have gravitational waves coming from, say, two neutron stars that are or have the last few orbits, or two stellar mass black holes very close to merger, then the frequency is about 100 hertz. So this is exactly the frequency range that LIGO or the ground-based gravitational wave detectors are sensitive to. If you have a gravitational wave coming from, say, a star, or say two neutron stars that are still very widely separated, or two black holes that are very widely separated, then we would talk about millihertz or decahertz. If you have supermassive black holes that are orbiting around each other, we would also talk about millihertz. So in fact, this is one of the items that we will discuss tomorrow to see the dependence on the frequency, how the frequency depends on the mass and orbital separation of our sources. Yeah.
More questions?
One of the improvements or proposed improvements from Lisa over LIGO was the fact that now you're adding a third test mass and you get to greatly reduce the spread on where the information could be coming from. If you were to add a fourth or a fifth or continue that into more test masses and or into perhaps even non-planar designs, do you think that there comes a point when the difficulty to maintain the system and or the noise that's introduced by having all this more complicated system outweighs the
You mean for Lisa specifically, or are you thinking
no extensions beyond Lisa? I think that Lisa now creating this closed geometry is fine, but then going beyond that, do you feel that this is something that becomes a little impractical?
Yeah, so if it's a space-based mission, yes, because you also have to weigh the gain essentially in scientific information to the cost that that you have by shooting an extra satellite up, right? So I mean, there were preliminary studies last year in the context of this ESA Voyage 2050 program, where we do think about designs for that can come after LISA. Not sure there were really serious attempts for more than 3 probes in there. So it's more, I think it was more about which frequency band are we interested in? And is laser interferometry still the technology that we would be thinking about in 30 years' time? Yeah, so I think I'm a bit wishy-washy here because the answer is I don't know, and it's something that one needs to think about very carefully. How much do you gain in knowledge versus, what the costs are? Because in the end of the day, we all need to get money from the funding agencies to actually build these instruments and send them up to space.
Thank you.
Does that kind of answer your question?
Yes, thank you. Thank you.
Mm-hmm.
Okay. Any more questions?
I had one question. Can you, maybe you'll talk about this later tomorrow or maybe the day after, but can you just briefly tell us how the strain function is derived?
Yeah, so
Is there some quantity that can be derived from first?
So that's what we will actually see tomorrow. If you have a source that has a changing quadrupole moment, then that will produce a strain. So what we will see tomorrow is actually how to relate the strain to the quadrupole moment of our source. Yeah, and I will go over one example with you, which is for a binary system. Okay.
Any more questions? Okay, if not, let's thank Helvi again.